All right, day 21. The monkeys are back. Each monkey has a job, yell a specific number, or yell the result of a math operation. So these are all the monkey names. They are very human readable. They either have a number or they have like the IDs of the two monkeys that need to like do whatever before they can get their answer. So we have to work out the number the monkey named root will yell before the monkeys figure it out themselves. So that wording feels really weird, and I don't know what they mean by it. I don't know when the monkeys are going to figure it out, and I don't think it tells us either. So each line contains the name of a monkey, a colon, and the job of that monkey. So we need to parse into multiplication, division, subtraction. So probably I64s, and then alpha 1. So we've got the name of the monkey. We've got the operation that has to happen. I don't see any like number times number, so maybe these operations are always going to be alpha. Let's take a look at the puzzle input. That looks accurate from a casual scan. Yada yada yada. 30 is the root monkey. No, 30 is not the root monkey. Yada yada. Root yells 152. However, your actual situation involves considerably more monkeys. What number will the monkey named root yell? Okay, so we got number 152. I just took a second to set up the files that we need and everything. 152 there. We're ignoring part 2. We are still, oh, I clicked the button. Cancel, cancel, cancel. Well, great. Access the debugger. That is not what we need. What did I click? Stop whatever that is. Close the panic. We know it's panicking. It's not supposed to run yet. Okay, what am I doing? I need to get the actual input. So here's our input that goes here. So I'm thinking about this problem, right? And it's very clearly in my mind a graph traversal problem. So we have some node. That node either has a number or it has an equation. And we do basically a traversal, a topological sorted traversal, which means that all of the edge nodes are going to get evaluated before the next thing that they point to. So we want to do a directed graph. We want to topologically traverse all of the nodes, and then we want to be able to get the root out of the end of that traversal. So this says to me, build a graph, use petgraph. Petgraph has a topological sort visitor, basically. And then probably we build up a hash map of all the results. Maybe that hash map grows too big in the second part, but who knows? We'll find out. The first thing we need to do is parse all of this in. So it's either going to be alpha 1, this is going to be one of the 4 operations, or an I64, I think is what we're going to go with, because we have to do subtraction. I think it's integer division. Does it say? It has to be integer division. I mean, it doesn't have to be, but like it would be really weird if it wasn't integer division. So we're going to stick around with that. So these two basically represent everything that we have to parse. So it's going to be something like fn nodes, input, string slice, I result, if I can spell. Wow. String slice, return value is going to be probably the graph. We should probably just return the graph here if I'm honest. So I'm just going to do unit for now and probably separated list 1, line ending, node. We pass the input here. So this would return a vec of whatever the node structure that we want to have is. Node doesn't exist, so we do fn. Because we're still using tracing, we can do instrument skip input. We never really want the input put out here because this is the root, but we can do fn node, same input. It's going to be a string slice or a node, and it's either going to be a name colon an algorithm or a name colon a number, right? So let's do this as like pretty basic. Let's call this ID. Let's do alpha 1 input, handle the error, let input, and then we'll go with, let's call this an enum that is operation. And it's either going to be a number, that's an I64, or it's going to be a calculate, which I'm going to put left string slice probably, operation. I'm just going to leave it as a string slice for the moment. And then right, which is a string slice. Of course, because this is an enum and because we're using lifetimes, we have to specify the lifetimes, which is totally fine because again, when we do this parsing, and Nom does this like basically zero allocation parser or like this thing where it returns us string slices, that input is going to come in from process part 1 and it's going to live until the end of the function. So if we borrow anything and we store it in an operation, that won't matter because input is going to live for longer than that thing is. So we've got an operation, thus we need a node, right? The node has an ID, which is a string slice, and it has an operation, which is an operation. Of course, when we do this, we see immediately that we have to do the named lifetimes again. So we'll do A here, and we'll pass A into operation like this. And alpha1 isn't in here, so we'll grab alpha1 there. I'll call this operation, and it'll be an alt for a complete I64, or it will be an operation. And then we'll return node from this, which will be ID operation, which of course has to be the OK with the rest of the input. So OK input, comma, but this is a tuple. And then I'm going to write an operation parser. I guess technically this is the operation parser, right? So do I need a separate parser here? Alt complete I64, and we would have to dot map over this for this to work. So this would have to be operation number num, and then operation, and this is returning an operation. So let's do, the other thing is that I forgot to do input underscore equals tag this. I'm splitting it out because it's a little bit easier to read and understand like that. I could do preceded the parser on the alt, but I'm going to split it out for now. So then we've got alpha1 on the left, and then we'll have alpha1 on the right as well. And in between, input, what do we call this? Operation equals delimited tag space alpha1 tag space. Input handle the error. Delimited needs to get imported. We'll import that. We go OK, input, operation, calculate, left, operation, right. So here we haven't constructed an additional enum for the positive multiplication, etc. We've just passed in that value. So I'm going to do, I'm literally just going to call this math. Multiply, add, subtract, divide. I'm going to map over this, and we're going to match, and it's either going to be star, plus, minus, or divide. And if it's anything else, I'm going to panic. And these are all going to be each of the things that they need to be. So math, multiply, math, add, subtract, and divide. And that changes the type here, which is going to be a math. We're just going to call it math. I guess let's call this operator just to differentiate it from operation, which will change down here because Rust is a typed language and it knows. It knows. So we end up with a separated list of all of our things. If we do let underscore, I'm just going to call this graph equals nodes input.unwrap, then we see that we have an issue here. So it's on the plus sign. Of course, we could add instrument to everything. So there, here, whatnot. And if we do, and now that they're instrumented, we see the error here, for example. It's a code alpha. So the alpha is failing. It's failing on the plus sign. So this is not actually alpha. So I think we can do one of. No, don't generate the one of function. I forget exactly how to type this. Import one of from characters complete one of. I think that gives us one of these, and these are all characters now, which is totally fine for us. And it panics at 80 here. So we can do info graph, but note that we can't do that either way, whether it's regular or debug, because we haven't implemented debug for any of these, which is something that I always forget to do. That means we need to derive debug, not debug dero, yada, yada. And then you can see now that we have graph with all of our nodes. And if we don't want to print it out like that, we don't have to, right? If we want to debug this out, just because we're using tracing doesn't mean we can't do that. So we can debug it and see it all pretty printed. So we've got the root node with a calculate between those two, number 5, number 2, HMDT. Do we have everything that we need? 32. Yeah, it looks fine. So we have everything that we need to actually operate on. We do actually need to create the graph now. So we do have a day where we build graphs. We have a couple of days actually. So if I rip grep for petgraph inside of our days, we got one on day 12, we got one on day 18. No, we don't have 18. 18, we didn't use it. It's just a dependency. You can tell because it's just in the cargo lock and not in any of the other files. So we've got to use petgraph, probably better. So we get day 16, we import it, and day 12, we import it. I think day 12 is the one with the ordered graph, if I remember correctly. Digraph. Yes, here's our digraph. So I'm going to snag this stuff because I think that's all we need. This is from edges, so we can do edges, right? So do we really want nodes to return the graph? I think we do. I don't think we need this as a vec at all. Doesn't do us any good to have it as a vec. So we drop all of our stuff in here like this. And then we make sure that we have our to do at the end to make sure that we don't light up with red. I'm going to pull in, am I going to pull in the dot config? Apparently it doesn't want to. Do we have petgraph in today? Cat cargo toml, or if I open cargo toml, it'll show me like this. If I do get dependencies, because this is new shell, it'll show me the dependencies. We don't have petgraph, so we need petgraph. It's just not, it's not cargo petgraph, it's cargo add petgraph. So that's why Rust Analyzer wasn't finding it when we tried to import it, but now Rust Analyzer can find it. So we don't have edges here, we have nodes. We've made each of the nodes into this operation. So this operation is going to depend on both the left and the right if it's not a number. So for the digraph map, we can use the IDs. So we're going to do string slices for the edge types, which makes this edge calculation significantly easier for us. So if we map over all of our nodes, we make this equal to edges, and let's finish importing while we're here. In this case, I am writing out graph dot dot every parser, which is fine. We need the trait for write all, standard IO write, if we're going to write all like that. So I think we're going to flat map this because every node that we have is going to probably have 2 parents, or it's going to have no parents. So if we match node.operation, then we know how many we're going to have to return. We can, using Rust Analyzer, fill the match arms unless it wants to do that, which it's been doing lately. I don't know why it's doing this up here like this, but let me just undo that. I think it's something to do with the macros. It's a new problem with Rust Analyzer ever since I upgraded to Rust 1.6.6. So I don't know if my versions are just out of whack or whatnot, but note that that thing that just happened did just happen. It replaced my macro on top of the function. And I've seen this also when using async programs. So there's a Tokyo macro that you have to use on top of your main function. And I've noticed it replace a fill match arms on top of that as well. So it's just a small bug. I'm sure it'll get fixed soon if it's not fixed already. I literally have not checked. So here we've got left and right, and we've also got the node ID. So we can do like this, and then it'll be from left to node ID and from right to node ID, because we need a directed edge from the things that we need to finish before us to us. And then for number, I think this is empty because there's no parents. So the other ones will take care of building the edges from the numbers. We'll make this a vec because we're running into an issue where each of these arrays has to be the same length. Again, arrays are not like arrays in other languages. Vec is the array from other languages. Yada, yada, this, and then match node operation. Consider borrowing here because data is moved because we're using node ID. And then from edges, string slice into weighted edge is not implemented for double reference to string slice and string slice, which means that these are double references. Yes, they are. So if we dereference them, then the test goes out of whack and we're panicking at 106. I think it's because we're writing this graph dot out. So we've already written that out. So I'm gonna stop writing that out and we can go look at it. And this is our graph. We can go check out one of those graph visualizers that we've seen before. So this is our graph, which is wonderful, that we just built from petgraph. It has all of the IDs for all of the nodes that are going to depend on other things. So for example, here we've got what I'll call human and div point. I don't know. PTDQ needs these 2 numbers to compute itself. And then LGVD needs PTDQ, which requires these 2 numbers. So if we do a topological sort, what'll happen is that we'll discover HUMN and DVPT before we discover PTDQ, before we discover LGVD, etc. So we'll be able to actually traverse the graph in the way that we need to. So I'll just get rid of all that debug stuff, and then we will input and graph as the return values. I'm just going to snag this type that we wrote here, drop it in here. And then we're left with actually a bit of a problem, because while we do have all of these edges here on the left, we don't have the data associated with them. And I haven't done the work to put the data into the graph. So we're going to do something like this, which is not the type that we have up here anymore. And to absolutely nobody's surprise, I'm going to translate this probably into a BTree map first of string slice to node, I think, right? So then we have nodes there, and we can do nodes.iter, or rather into iter, right? And we map, we get each of these values, which is an individual node, and we map it into node.id node, and we collect it, and we shadow the node's name, and we make sure we get our semicolons in, and then we get through. And if we go scroll up beyond the graph, we end up with a BTree map from the ID of the node to the operation we need to actually calculate. So here we have operator and it's highlighted in yellow. If we aren't going to use this, normally what we're used to doing is putting an underscore below it, but because we're destructuring here, so we've got operation calculate and we're destructuring these fields in this match, we have to say that we're not going to use it like this instead. So we still use the underscore. We just do operator colon and then the underscore, kind of renaming it. We also don't need num here, but we aren't actually matching on anything named num, so the underscore before will work. So we've got BTree and graph, and that means we need to do our topological sort. My browser history took me to petgraph algo, so I just need to do Toppo. Basically, the way that you would get to this otherwise is in petgraph, there's a module here called visit that says graph traits and graph traversals. So if you click on visit, you can see all of the ways that we can traverse over a graph. Depth first search, breadth first search, some variations on those, and then Toppo is actually the one we want. So Toppo is a topological order traversal for the graph. So we can import petgraph visit Toppo. We can do new with our graph. Of course, if we are iterating over this, we don't need to pass it in. So into neighbors directed is not implemented for the actual graph map itself. And you can think about, without knowing anything about this trait, right? We got to take this graph and implement a trait called into neighbors directed, which takes the graph and turns it into the neighbors using the directed information. So a directed graph. But to do that, we have to pass in the shared reference here instead, which it is implemented for. So if we try to iterate on this, it's going to tell us that we need to implement the walker trait, which we do. We need to pull that in. The walker trait takes, or the iterator anyway, takes an argument. So iter takes a context, create an iterator out of the walker and given context. So if we use the graph as the context, then we can iterate over this with the graph. And for every node, we can debug out the node. We get all the node names in the order that we need to see them. You can see root here at the end, PPPW is another one. So if we look at the root, which is up here, then we see it depends on PPPW. So we would expect it to be one of the last ones that we see in this list. So if we create a cache that is a BTree map of string slice to I64, then for every node, we can match on BTree, which is the original .get node. I guess we should call this node ID, right? It's not actually the node. So if we match on this, which we actually don't have to do now that I think about it, unwrap, the match comes later. If we match on BTree get node operation, that makes more sense. It's a bit much. I'm going to copy and paste this again because it blew out my macro. I don't know why Rust Analyzer is not participating in this. So we borrow here, everything's fine. And then we get either a number or an operation. So if we get a number, then we do cache.insert node ID number. And we add our semicolon there. And number needs to be the value, not a reference to something. Otherwise, we get into calculate, we match on operator, and we drop this in, and we either get multiply, add, subtract, or divide. This is all going to be the same stuff again. So we're going to write it all at the same time. And then the only difference is that we get the left value, something, the right value, not num, the right value. There we go. So for multiply, we multiply. For add, we add. We can subtract, we can divide. And did I do something wrong? Did I make assumptions that don't hold? Left and right. Left and right are the nodes. Of course they are. The node IDs. I totally forgot about that. These at this point should have each of their values. So let's just define these outside of insert. We'll do, I don't know, left value, I guess, equals cache.get left.unwrap. And we do the same for right value. And that works for this. We don't need the dereferences because we're doing this get, I think, but we do need basically this again instead of what we just wrote. So I'm just gonna clock this in here. This is add, this is subtract. I guess we could have done this outside of this too. That's so silly of me. Let's do that. Instead of doing this in every single match. Why am I doing that? Sometimes you just get started doing something and you're like, ah, yes, this is going to work. And you're not wrong, but it's not the best way either. So we can do left value and right value here, right? And we don't want to cache insert up here. We're going to take this and do cache inserts down here. Now this is add, and this is subtract, and this is divide. And I'm sure there's a like tighter way to write this code, but I'm just going to leave it pretty verbose for now. We get all the way through to 170, which means that we get cache.get root. We need to unwrap, of course, because get returns an option. and then we need a toString, and part 1 works. So this gets the root value. So what do we do here, actually? We constructed a BTree because the access patterns that we're going to do later allow us to get each of these nodes by ID, basically. So the BTree is our store of data. The graph is our store of the relationships between that data. Because we have the relationships between the data, we can do a topological traversal of that graph. And that means this iterator right here will traverse from the edges in, only hitting the next value after it's hit all of the parent values, if you will. We of course need this cache here as well, because this cache is what keeps track of all of the populated values, basically. So for every node, we are going to end up with a value, and this is how we populate that, the result of the operations, basically. And at the end, we're left with the cache has the value of root after we've calculated everything, so we're good. I really feel like I should do this video again, because this topological sort stuff is really cool. And I think we could make a really nice, concise video for like how to throw things into a graph and get that topological sort of these values. And there's a lot of really interesting stuff here. And I don't think that people use graphs very often. So we're left with all that. Cargo run bin part 1. It gives us a number. I am concerned that this number is large, but we did use I64s. So I'm hoping, yes, and that's correct. So part 1, throw it into a graph, topologically sort it, iterate over that topological sort, get your result. Part 2, due to some kind of monkey elephant human mistranslation, can't imagine how that happened, you seem to have misunderstood a few key details. First, you got the wrong job for the monkey named root. Specifically, you got the wrong math operation. The correct operation for monkey root should be equals, which means that it still listens for two numbers from the same numbers, but checks that the two numbers match. Second, you got the monkey wrong for the job starting with HUMN. It isn't a monkey, it's you. Oh, it is human. I literally called this human earlier. Actually, you got the job wrong too. You need to figure out what number you need to yell so that the root's quality check passes. The number that applies after HUMN in your input is now irrelevant. Okay, so we have a calculation where human is X and the number we need to pass is 301. So what, everything above human is irrelevant? Is that true? Is human even, where's human is 5? Okay, so human needs to yell a value. So do we need to reconstruct the graph to reverse this, basically? So we need to run one half of the graph, and the other half of the graph we basically need to hold. And then when we get to root, then we need to reverse all the math that we were supposed to do to calculate the last value. So I think we do something like traverse over everything, store all the node IDs that are in the first half of the graph that we're not going to calculate, and then basically reconstruct a second graph. If the values in the first iteration don't exist, we just skip them, which means they're in that path, right? The human path. And then in the second iteration over the second graph, we just do it in reverse. Basically, we reverse all the edges and then work our way outwards to human. So 301 is the number that we need. So let's start working on part 2 here. Let's grab all of this because I feel like it's still pretty useful. And then this does a calculation for everything, right? And if we have a number, we should insert it. That's correct. If we have a calculate, unless it's human, unless it's HUMN, right? If node ID equals HUMN, do nothing. Well, let's do it this way. If node ID is not equal to human, then we insert into the cache. Because that's a number, because we will just have a number, right? And then for the operation calculate, I feel like there's going to be a number of things that we can calculate. And the only tree that we're going to have left is the one that we can't with the human. So we're going to end up with like one line from human to root, no matter what we do here, because everything else is going to be calculatable or calculable or however you pronounce that. So we've got the left and the right value. These are no longer unwrap because it could be that these are not available to us. So we do let sum left value, right? Equals, we're just gonna shadow these names to make it easy for us. And we're gonna do an else here, I think let sum equals, that's not right. The sum needs to be inside here. I guess we need to match here though, because do we need to match? Let's see. we're doing let sum left value, sum right value for left and right value in a tuple. If that is not the case, if we don't have them, then one of them is none, which means this node ID that we're working on is one of the node IDs that we need to work on later. So second graph, can we just draw the edge in here? So left and right value, right? We've got a node ID. We've got the left and right IDs. We need to draw in the opposite direction, basically. So where we built up our graph up here, right? Where is it? It's here. We built up our graph up here doing left to node ID and right to node ID. We're going to flip these, basically. So let's do another directed graph map here. And this is going to be second graph. And I think we just do new here. And this is going to have to be mutable. And then we do second graph dot add edge, which is node ID left. I don't think the weight matters. I think the weight can be unit. It is not happy with that. Let's get tests running so that we can see our errors. Expected exclamation point found unit, right? Can we only, I guess we have to do unit out of this. Interesting. So let's grab this anyway. Let's get rid of this. If let sum from this, then this match runs. Else this graph insertion runs. So second graph, add edge, node ID left, and then we need to do the same thing here, node ID right? So we build up a second graph, we build up our cache. Hopefully we've skipped the values that need skipping. And then this is our whole iteration here, which we could probably pull out into a different function at this point. It's getting pretty long, but let's debug second graph here. And we've got a root incoming to SJMN. Yeah, so root goes to PPW and SJMN, which are the ones that we need to figure out. It is interesting. Have we kept too many things in here is my question. Let's get the dot going. Let's visualize this. I really like the ability to visualize this because it makes looking at things like this a lot easier. All right, so let's get our dot going. I don't think we need to print this out. And this is probably freaking out because it's already writing, because we're running the tests. And if we look at graph dot dot, I think this is the result, right? I think so. So this is the one that we were looking at, right? This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 nodes. And the second graph that we just got is the same graph. So that's wrong. So it didn't write out, I guess. Oh, that's because I'm passing in graph, of course. Where is it? Second graph. That's why, because it was the first graph. That makes total sense. So we look at graph 2, it looks like this. Let's look at these side by side. Side by side would be fun. So this is what we get. And each of these values are going to have cached values, right? So if we do the traversal here, then we have root at this point. Why am I zooming in so far? We have root, right? Which means that PPPW is the reverse from SJMN and root, right? So is this actually going to work, just reversing the edges? If we get the nodes, right? If we get node PPPW, what does node PPPW have? PPPW has CCZH over LFQF. So it has these two. So if we have root, right, for example, and we have SJMN, so we're going to start with root probably on the topological sort. Where's root? It's always on another line. So we have root, right, which is going to be 150. And we've got this plus that. So it's going to be, we're going to have SJMN. So it's going to be root minus this thing. I think the only one we might trip up on is this. So if we do the left value when we topological sort and iterate, and we insert the left value into the cache as root opposite value SJMN, then we keep going down. And when we get SJMN, if it already exists, right, because eventually we're going to get here and we're going to see some value. If it's in the cache already, we don't recalculate it. That's not going to work though, because that will also work for root, because root's already going to be in the cache. Do we need to build up an alternate structure as well as the alternate path, right? If we build up a new set of nodes, so it'll be a new node, and the ID will be root, right? And the operation, if we, because we're just avoiding putting them into the cache right now, but we could be, when we avoid putting them into the cache here and we creating these edges, we could be reversing it. I think that's the issue. I think we've got second graph add edge, right? But one of these values we have. Which value do we have? Is it always the right one? We can check, of course. We probably should check, which turns this into a match above though. So this is an if let right now. I think we need this to be a match. And then we do this, we match on this. The first one is going to be this sum for both of them. And then we go down here and this is none, right? Let's comment that out. Expected string found unit from parse part 2. Yes, that's true. We aren't really returning anything anymore because we need to do this. Cache get is going to be human, right? This is expected string found unit at, this is the downside of what I just did. That's the inner match, right? The match is returning unit. This is the next match. This is the outer, right? That's end match. This is operation calculate. This is match, and then we got 4. So we've got operation calculate, match, and then we've got 4. So we needed one more curly brace. And we have an issue with left and right. Pattern is not covered. Yeah, we still need to deal with that. So we've got some, we don't care, none, right? And some we don't care, but none is before it. And let's just do a little test here. I have a suspicion that none is never going to happen. Yeah, B. I think none is never going to happen. So let's just ignore that case for a second and call it none. And then we have A and we have B. So if we have A, what edges do we need to build? We have, say, the node ID to right, and then also left to right. I think this is it. I think this is the answer. And then for the other way, we end up in the opposite direction. So this is going to be left, and these are going to switch. And then 270 is whatever on a none value. That's fine. Let's now look at our graph. So we wrote out graph 2. This is our new graph 2. This is our old graph 2 on the left here. It's got a root that points to 2 children. We want it to be the other way around. We want root and SJMN to point to PPPW. So root and SJMN are values we have. PPPW is a value we need to calculate. Same way all the way down until we get to human, which will give us the answer. So if we do it like that, then we can do our topological sort. We're going to do basically the same thing, right? I'm going to put this down after this giant comment just to separate these a little because I'm not doing the greatest on my code organization today. We could probably pull this out somehow. Second graph. We need a topological sort for our second graph, but we're still going to use the same cache. So second graph here, topological sort. If we iterate over those, we no longer care that this, well, if it's human, we still don't insert the cache here because we're calculating numbers basically now, right? So we are going to what? Print these out. That would probably be useful. It's going to go root SJMN, which are both numbers that we have, down to DVPT. We never get human, notably. 287. Why don't we ever get human? Oh, do we never? Because we need to do an insert here in the other one for human. That's what we need to do. So we've got these, right? And then up here, we've got a number. Human is a number. So we don't know. Do we not have human in this graph? We do have human in this graph. PTDQ and DVPT. Why don't we see human in the output? Topological sort, SJMN root LF, SJMN root LF. We don't see PPPW either in the topological sort. Why is that? Is it not in the graph? Let's debug the graph quickly. I think it has to be in the graph, right? We just looked at this. Root, PPPW, yada, yada. Human. Human's right there. 2 incoming. Why is this a node that we don't get in the topological sort? Oh, because we're iterating over graph. Oh, man. The context that I passed in was not the right graph. That's why. See, now we see human. Okay, so we get SJMN root PPPW, SJMN root PPPW LF. Yeah, that looks good to me. And then we have to match on these, right? This is match operator. I'm just going to copy this whole thing right here. So we get this. We don't have these anymore. We do have to do a cache insert, but we have to get the values first, right? So let's do a closing brace here, an opening brace here, and then drop these in. Still runs our match. So we get the left value, we get the right value. We don't know if we have either of these yet, right? What we really need, I think, is the root value. Get the node ID. This will always exist, so we can unwrap it. I don't know that we know which one of these is going to exist. Does it matter for anything? For addition and multiplication, it doesn't. For subtraction, we get different numbers if we do it in the wrong order, right? So if we've got the node ID, and let's say we're trying to find left, and we know left minus right equals the node ID, then node ID plus right equals left. But if we're trying to get right value, then it's node ID. I'm going to pull up my 4th grade math for a second. If we've got 5 equals x minus 3, then we've got 2, right? That's not true. That's 8. Wow. I just failed basic addition. So x is 8 in this case, which we can calculate by doing plus 3 on both sides. Huzzah, I passed 3rd grade math. If we have 5 equals 3 minus x, then x has to be -2, right? So it's still, what do we have to add? I think that's what it was. It was a multiplication by -1. So it would be -3 plus x equals 5. That's not true. Equals -5. So it's a multiplication by -1, and then, wait, this is, did I say plus right value up here? If it's left value minus right value, then it's plus right value. Then it's times -1 plus left value. So if we've got 5 equals 3 minus x, we multiply everything by -1, then we've got a positive x, which means we take the left-hand side and we add it to 5. We take 3 and we subtract it from 5. So it's -5 minus 3, which is effectively -5 plus 3, right? So it's this equation. -1 times node ID minus -1 times left value equals a positive, equals x, which is, in this case, -5 minus -3 is -2. And if this is 1, then it's -1 equals -3. So -1 minus -3, so plus 3, is still 2. -1 minus -3 is 2, which is 3 minus 2 is 1. Yes, okay, that's correct. So these are our subtractions. I'm just gonna leave these here. Why did it take me so long to work that out? That's so silly. Welcome to being somebody who has to stream and talk and do stuff at the same time. Now we have to do the same thing for division though. So I guess we do the match in here because this matters, right? And we do sum L none. What are we matching on? Left value and right value. And we fill the match arms, which works this time. And if it's sum, I think we've done something wrong, right? Because we are trying to calculate sum value here. If it's none, we've also done something wrong. Because in either of these cases, that means we have no numbers to calculate with, or we have all of our numbers already, both of which are not going to happen. So we've got R and we've got L. R, if we have R, then this is, do we have the node ID value? Did I get that? Root value. Okay. root value plus R. And we have to insert that, reversing math. Okay. We have to insert root value plus R as the left ID. And if we have the other thing, we have to do something like this, but we'll be inserting right, and it will be -1 times root value minus -1 times L value. Let's do the multiply ones next, because those are, for multiply, it's whatever over the other one. So these are still panics. This is insert left root value over R. This is insert right root value over L, right? Because if we're multiplying left and right to get root, then root divided by either of them is the other. Same thing for addition. So I'm just going to copy this in again, and we're going to get minus for these. And then we've got division. Yay. So for division, right? So the division was left over right. Root equals left over right. That was the division that we did to get to the root. To reverse that, if we need to get 10 equals 100 over right, if we don't know the left side, this is much easier because we multiply by the right side. So if we don't know left, multiply by right. If we don't know right, the equation is multiply by right. So it's 10 times right, and then it's left over root. 368 expected expression. Sick. Everything formatted. At the end of all of this, we need to get human at some point, which is going to be this one, right? So this will be calc human. And what do we have here? Node ID. Second graph is all of this. What is human? Human is PTDQ and DVPT, which we should have numbers for both, right? Because we're panicking at 309. Oh, we can't do the root calculation, can we? Root is always 1/5, or root is, we're doing root wrong, I think. Because if we get it in between, right? If we don't do second graph here and we do debug cache.get root, I think we're doing root wrong because root has to be 150, which I don't think it's going to be. Cache get root is none. So maybe we cache insert root, and that would have been whatever the value that was going into root was, right? So we probably have to do it up here. Where is, I think root becomes a calculate, right? So we can do an if root here. Yeah, root is a calculate right here. If node ID is root, debug node ID left, right operator. And I think we just need to change this, right? It's just the equality. So we just set root to be 150. No, we set the right-hand side to be 150. So one of these is going to have a value, right? So left value none, right value 150. So the left value needs to be 150 for them to be equal. Of course, I don't know which one is going to be empty. So hopefully, I bet you the part 2 input just switches this randomly. But we do the match on left value and right value. So we get all these. If none of them exist, we've messed up. If both of them exist, we've messed up. If the right side exists, then left cache.insert left R, right? Because they need to be equal. And this will be dereferenced. Is that right? Cache.insert this and that. And we need to wrap all of this rest in another level of nesting. I think we can just continue here, right? Which solves our issue. So we had a mutable borrow issue right here. Mutable borrow occurs here. Cache insert left, right. That's because we do it here and then we do it down here as well, right? 206 is where it says whatever. So left here is an option. Left is not actually what we want. Well, it is. Left is not an option. Left is a double reference to a string or a string slice, sorry. So we mutably borrow, we do a cache.get, right? Left value, which gives us the left value. That's a reference into cache. We get the right value, reference into cache. We match on them and then we do a cache insert. This is a mutable borrow of the cache that we just got these values out of. We could clone these, right? Totally fine. We also use them later. So we're holding this shared reference over the period of time where we're trying to take an exclusive reference. But if we do continue, Rust knows that we are not going to run the rest of this for loop, and thus this continue fixes that problem for us, because when we hit this cache insert, we won't be holding the shared values till this point because we'll never get to that point, right? This code won't run if we hit continue because continue will loop through again. So we need to do the same thing if it's the right value. At which point I'm not sure if our graph is correct anymore. 401, not implemented. This is a lot of code. So I removed the to do and our part 2 test passed. So I think that we did all of our reverse math correctly, at least for the test case. So let's try to run it on the actual input then. We panic at eq on 345. So 345, we have 2 values at mhjp in our input. So mhjp is HSBN and FPLT. Doesn't tell us a lot, probably somewhere deep in. So I'm not even going to try to look for it. If we have them both and we're adding, right? This is the reverse section. If we have them both and we're adding, which value do we need? Let's do a debug node ID left value, right value. And maybe we do root value here, right? So we run this and we get root value 27, sum 5, sum 22. So maybe we just let this go because these values are already correct. 5 plus 22 is 27. So we don't need to necessarily panic here. We can just let this run. And then we panic at eq again on 389, which is probably the same thing, right? If we already have these, then why are we stopping it from working? And we panic at eq at 325, which is probably the same thing because we have this in all 4 places, right? So if we have both of them in all of these places, is that the last one? Let's do here too. Actually, let's just make sure we hit this one because that's interesting. So that is 366, which is this one. So if we already have them, then why do we even bother recalculating them, right? So we have this number for human. This seems like a large number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think that counts. That's the right answer. Haha. So our reverse graph approach worked. The hardest part of that for me was my 3rd grade math, unfortunately. So that worked for part 2. So let's go over what we did, right? Because I spent a little bit of time in the weeds here, and it's useful to go over the overarching result. Let me get rid of this random debug here. We'll get rid of calc human too, because there's nothing we actually need to do for human because we've already calculated it by the time we get to it. So if I run this again, we should get no output except for the correct output, which is great. So I think that it's useful to take a look at these graphs probably again. So let's make sure that this gets written out. Let's write it out for the test because the test will be easier to understand. Let's minimize that. Let's grab our editors. So on the right-hand side here, I'm going to put in the resulting reversed graph. And on the left-hand side here, I'm going to have the original graph. The second problem is basically that we are going to get all the numbers for the left-hand side here. So HMDT, DBPL, DRZM, SJMN, we're going to have all of those. Those are all going to calculate just fine. But the right-hand side, HUMN, is actually, I am not working the Zoom very well. HUMN is X, basically, in our equation. So we've got this giant equation where HUMN is some number that we don't know, and the root calculation is SJMN and PPPW have to be the same value. So in this equation, we have some X. We don't know what the equation is before we read in the values, so we have to kind of like work backwards to it. So we do the same thing we did in part 1. We do a topological sort. This allows us to do HMDT, then ZCZC, then DRZM, then DBPL, then S. It does a sort from the outside in, making sure that anything that we need to hit before we hit, say, this node, for example, is hit before we get to that node. That allows us to calculate this entire branch down to SJMN. Then what we need to do while we're calculating or trying to calculate everything from human down is we need to take these and we need to reverse some of the arrows, right? So for example, to get human, if a human is X, right? DVPT and PTDQ, the two nodes that are next to it, need to both point back to human. So as we traverse down from human, from DVPT, from PTDQ, and so on, down this topological sort down to PPPW, we're building up a second graph that looks like the reverse of what we got. So we end up with a second graph that's PPPW, LFQF, and you see these, and they both point to CCZH. The reason they point to each other in this way is depending on the calculation that we need to do, right? So if we have PPPW and LFQF is a number, then CCZH needs to be calculated from PPPW and LFQF. So that's why we're drawing the arrows like this, because CCZH is the value we don't know, whereas PPPW and LFQF are numbers, just like in the very first part 1 that we did earlier and in the left-hand side of the graph. Now, when we traverse the graph on the right that we've built up, the second graph, what we need to do is we need to reverse all of the math that we would have otherwise needed to do. So for addition and for multiplication, this is super easy. It's just remove the one that we have from the root value. So if, say, the node ID is PPPW, or let's say we've got PPPW, right? And we've got LFQF. And before, PPPW told us that we needed to add CCZH and LFQF to get PPPW. Well, now we need to subtract LFQF from PPPW. And we do that for everything. So the addition and multiplication are super easy. It's either PPPW minus this or PPPW divided by this. For subtraction and for division, the ordering matters. So we have to do slightly different operations for each of the nodes, but we do basically reverse math all the way down until we get to PTDQ and DVPT. In this case, I think what we actually end up with is DVPT as a number and PTDQ as a number, which was calculated from these two parents. So when we get to human, we actually already know what the answer is. So that's the approach. Functionally, the way that we do that is we parse the nodes from the input string, which are just the node and the operation, right? Basically, we get a B tree of all of the nodes and the operations or the numbers that they have, as well as the graph relationships between them. We do a topological sort of the graph that we've created from those nodes and from their edges, and we set up a cache. This cache is going to cache all of the values that we've calculated before we go over this tree, right? So theoretically, we could prime the cache with the numbers that already exist. We don't really need to do that because when we do the topological iteration, those numbers are already numbers and we will hit them first, so we can just insert them when we go over them. Now, we also need to construct this second graph, this reverse graph, as we are traversing. So we construct a new second graph that is also a directional graph. We match on the operation that we need to do for every node in the topological sort. For numbers, we just insert them into the cache unless they're human, because human is X, but human will come in as a number because we haven't changed the actual values. We're just told to ignore it. It's either going to be a number, which we can insert into the cache, or it's going to be a calculate, which we can then check to see which values we have and deal with appropriately. Now, we need special handling for root specifically, because root is going to come in at the bottom edge of our graph, for lack of a better term. It's the only operation that needs to be equality. What this means for us is that the nodes that point to root both have to be the same value. If we think about this in terms of the graph that we constructed and viewed here, that means SJMN is going to have a value and PPPW needs to be set to that value. And then we can just tell root to scurry off and we don't need to use it. So when we start the traversal of the reverse graph, PPPW has a value. It has the value that SJMN had. That's what we're doing here. We're setting PPPW equal to the value that it needs to be. We're at root. We already have the other value, whether it's left or right. So then we can insert. For every other regular node in the graph that isn't root, we match on the left-hand value and the right-hand value. This is the straightforward math approach as we're going down the graph. So if there are two values here to do with, which will happen for the entire left-hand side of the graph, then we take the left-hand value and the right-hand value and we do whatever we need to do. We multiply, we add, whatever. We insert that as the value for the node ID that we're processing. That's the straightforward part. If we only have one of the values, that means we're somewhere in the right-hand side of the graph, right? Because on the left-hand side over here, we're topologically sorted. We're getting the numbers HMDT and ZCZZ before we get DRZM. But on the right-hand side, HUMN isn't in the cache. So that means everything that's affected by HMNN going down to the root is going to have one of the values missing. We write this so that it works for left-hand side and right-hand side. I don't know how necessary that was, but I don't know what the input was going to do either. So this is the same code basically. So if we got sum none or none sum, this is the same code. We're adding an edge to create that second graph if we only have one of the values, because it means that we have to process that node again later in the opposite direction. So this is where we reverse the arrows. So we add an edge from the node ID to the right-hand node and from the left-hand node to the right-hand node. That's how we get CCZH here getting pointed to by PPPW and LFQF. Whereas in the original graph, CCZH pointed to PPPW alongside LFQF. So that's the change we're making between these two parents to PPPW, so that PPPW is a parent with one of the arms, basically. And that happens whether it's the left-hand side or the right-hand side that is missing a value. If we don't have either of the values, then we've messed up because only one of them should be missing at a given time. So at this point, we've traversed over the topological sort of the entire graph. We've built up the second graph. We've processed the left arm of the graph into a number, and we are ready to start processing the reverse direction to find out what human is. So we do the same topological sort on the second graph. We iterate over that sort with our second graph context, and we match on the BTree to get the operation that we need to do. If it's human, then we do nothing. If it's not human, then we insert any number that we have. And if we look at it, that does happen a couple of times. We do have a couple of numbers that we can insert. Now, an interesting note is that these do already exist. So if we didn't run insert here, our test still passes because these actually do get inserted in the first pass. So we could actually do zero processing under number if we wanted to, because when we went through the graph the first time, because we're using the same cache, we inserted all the numbers we had, which means that we don't actually need to do anything here at all. Otherwise, we get calculate, right? So we have to do something. We get the root value from the cache. That is the node ID we're trying to process. Remember, the node structure hasn't changed. So the node ID in our node struct still points to the left and right values like it would in the original graph. So in this case, we know that we're processing it differently. So we get the root value and we try to get both of the left and right values. We know the root value will always succeed. The left and the right values, either one of them might fail. So if we then have to run a multiply, we have either a left value or a right value. For multiply, it's much easier than the other two. We insert the value we don't have calculated from the values we do have. So for multiply, it's root value over the other side, whether that's the right or the left. Same thing for add. If it was going to be left plus right equals root, now it's root minus right or root minus left to equal the other one that we don't have. And this goes through and we do the math here that we have to do for subtraction and division as well, except subtraction and division are location dependent, right? The order matters. 3 minus 2 is not equal to 2 minus 3. So we have to calculate each of the values slightly differently to reverse it. Now, there is a situation that we get to in the actual input where we end up having two numbers already. If we already have two numbers, we get a free pass. We don't have to do anything. Those numbers already exist. So we're good. So in every one of these, if we have two numbers, we pass it through. It's fine. If we have no numbers, that's a problem. We've done something wrong. So we've traversed the graph the first time, we've traversed the second graph, and then all we need to do is get the node that we care about, which is human or X, and we toString it, and we're done. So this was a really fun day. I really liked the graph search here. It's relevant to some work that I'm doing in other places. So this was a really exciting day for me. I had a lot of fun, and I hope that you had fun as well. Learned something new maybe. Let me know how you solved it down in the comments, and I will catch you in the next video. Have a great day.